Alright, we're beginning online class 8, section 6.2, standard normal distributions, and it's Friday, October 19th, fall 2012. And this is Carl Perez, SUNY Cobleskill. We're going to start a new chapter today, and it's entitled Chapter 6, is entitled Normal Probability Distributions. Alright, I want to talk about what it means to be normal before we go on in earnest in section 6.2, kind of a motivational introduction as usual. I want us to recall chapter 5, which we just finished, of course. The title of chapter 5 was Discrete Probability Distributions. And I want to talk about, for a minute, what it means to be discrete. Let's say I ask us, we've done this before in class, let's say I want you to construct a probability distribution for x, where x equals the number of girls in 3 births. Now, we've done this in class many times, and actually a few different ways, both using the brute force method and the binomial probability formula. Of course, we can call this a binomial probability distribution with, let me write that down, we're going to use the binomial Cdf command, and with number of trials equals 3, assuming boys and girls are equally likely in any birth, we'll say the probability of success, meaning a girl, in any one trial is 0.5. And x, of course, the number of girls can range between 0 and 3. Alright, you recall we've done this several times before. I just want to highlight something here. Maybe some of us even got this memorized. Alright, the probability of 0 girls is 1/8. The probability of 1 girl is 3/8. The probability of 2 girls is also 3/8. And the probability of 3 girls is also 1/8. Alright, what I want to highlight here is this is a discrete probability distribution. Alright, what do I mean by that? You'll notice that x can take on the whole number values 0, 1, 2, and 3, but x can't be anything in between those values of 1, 2, 0, 1, 2, and 3. So let me write this down. Values of x, possible values of x, are separate and discontinuous. Right? Meaning the x values are not on a continuous scale. X can only take on separate and disconnected values in the range from 0 to 3. Right? And that is the meaning of a discrete random variable. Right? So let me write that down. X is a discrete random variable. And in the realm of mathematics and statistics, that's what discrete means. Right? Discontinuous scale. X occurs on a discontinuous scale. Let me write that down. X is discontinuous. Alright. Alright, well, what do we do in the case when we've got a continuous random variable? How are we going to assign variables in a continuous random variable when the only way we know how to do it so far is with a table, and you can't list infinitely many values of x in a table, as you know. Let's talk about what it means to be a continuous random variable. give you some examples. X, for example, could be the speed of a car. And let's say the speed limit's 55 miles per hour. And X can be anything in that range, between 0 and 55. And we're not just restricted to integer values of X here. So, as you know, between any two values on a number line or a continuous scale, there are infinitely many possible values that X can attain here. So what I'm getting at here is we can't use a table to construct probability distributions in this case. Write that down. Probability distribution. Alright. Well, how are we going to do it? Well, typically what we do to construct a probability distribution in the continuous case, we do it graphically. What I'll do is, well, let's say we've got a continuous scale of X values. And if I describe the behavior of X between any limits of interest, I can draw what I call a probability density function. Probability density function for which the area underneath this curve, this probability density function, is 1. So we're going to make a link between area and probability here. Oh, looks like a G or something there. Total area under, just abbreviate it like that, is 1. And if I'm looking for, let's say, the probability that X is between, say, value A and value B, I can then figure out or grind out, using techniques of calculus or the TI-8384 calculator, the total area under this probability density function between the limits of interest A and B. So this area will be the probability that X is between A and B. And I can symbolize it like that. Okay? Alright. Now, we will use either calculus techniques or the TI-8384 calculator to grind out these areas. Now, as you know, calculus is not a prerequisite for this course, but again, the TI-8384 has got the capability to calculate, using calculus, the areas under curve, under a probability density function between any two limits of interest. So, of course, calculus is not a prerequisite for this course, so these long established formulas are burned in to our TI-8384, and we're going to use that function to find these areas. Alright, let's not get too far ahead of ourselves. I want to talk about the normal distribution in particular. Alright, a normal distribution is a continuous probability distribution. In other words, it's based on a continuous random variable. And if we draw a little picture, we've already kind of drawn one for you. It's typically what they call the bell-shaped curve. Based on x values that can range theoretically anywhere between negative infinity and positive infinity. Alright, x is a continuous random variable. As we mentioned before, x occurs on a continuous scale. You'll notice the normal distribution is symmetric. What do I mean by that? Well, you've got vertical symmetry about the vertical line x equals mu, where mu is the mean of the distribution of x. Alright. The total area under this normal distribution equals 1. And again, we can make a convenient link between probabilities then and area under the curve. Please note that the bell-shaped curve always peaks at the mean. The mean value, or any value near the mean, is the most likely value of x. Alright. This PDF, this probability distribution, is based on a formula. It's in the book, and I won't grind it out here. It's really beyond the scope of this course. It really requires calculus to fully understand. But again, we'll say that it's burned in. This formula for this curve is burned in to the TI-8384 function capability. Let me give you a quick example here how we use this TI-83 to grind out these probabilities. Let's say, suppose we have a normal distribution with a mean of 0 and a standard deviation of 1. And I can easily draw a normal or bell-shaped distribution where the mean peaks at the random variable value of 0. Right? If I want then the probability that x is between 0 and 1, well, all I really need to do is use either calculus or the TI-83 calculator to tell me the area under this normal distribution curve between 0 and 1. And again, the calculator will compute this for us. I'll show you how in a couple minutes, okay? Alright, so when we say normal, we think bell-shaped, right? I suppose that's the big thrust of what we've talked about so far. Alright, there are many different normal distributions. Really infinitely many. Remember, normal means bell-shaped. Let's say we give a test in a class. And let's say we give a test actually in 3 different classes. And let's say we've got class 1 that takes the test. And their mean is 70. And their standard deviation is 10. Let's say, let me try to get another color here. Let's say class 2 also takes the test. And they get a mean of 60 and a standard deviation of 5. And let me get another color here and talk about class 3. Let's say class 3 takes the same test and gets a mean of 80 and a standard deviation of 20. Alright, assuming that these classes all have a bell-shaped distribution of test scores, I can attempt to graph all the distribution of scores on the same scale And I'll do my best here to do it kind of freehand. I'm going to do class 1 first. Class 1 has a mean of 70. Okay, so that means their bell-shaped distribution, their normal distribution of scores, will peak around 70. Right? Let's look at class 2. Class 2 has a mean of 60. Well, down here somewhere. And a standard deviation of 5. So it will still have a bell-shaped distribution, but it's going to be a tighter distribution because the standard deviation is less. So I'm exaggerating this a little bit. So my distribution of class 2 scores would look something like this. Still bell-shaped, still the total area under the curve equals 1. It's shifted down from 70 with a tighter bell, I guess you'd call it. Let's do class 3 now. Class 3 has a mean of 80. Well, that'll be up here somewhere. Notice, right, their bell will peak at a different score, right, of 80. And the standard deviation is 20, which means a wider spread. And their distribution may look something like that. Alright, so the long and short of it is there's some fat, skinny bells, there's some short, fat bells, but in the end, any normal distribution will have a different bell shape. Alright, and again, the location of the bell, the location of the peak, the highest point on the curve, will always be at the mean of the distribution of test scores or whatever variable we're interested in. Okay? Alright. Let me write that down. I'll go back to yellow here. In a normal distribution, the bell peaks at the mean. That means scores near the mean are the most likely scores, and the standard deviation determines the width of the bell or the spread of the bell. Okay? Alright, let me get a fresh screen here. Alright, and as we know, there are very many, really infinitely many types of normal distributions. Short, fat ones, long, skinny ones, in-between ones. But there's one very special one. Alright? And that we call the standard normal. Alright, and what's special about the standard normal distribution? Well, the first thing it is, it's a normal or bell-shaped distribution. But please note, the mean is 0 and the standard deviation is 1. If you've got a normal distribution with these parameters, then you've got what they call a standard normal distribution. In fact, this distribution, this particular distribution, is so special, we reserve a special letter to designate it. Reserve the letter Z for a standard normal. So anytime you see the letter Z, we think standard normal distribution, and anytime you see standard normal, you know you'll signify it with the letter Z. So I usually abbreviate it like this. Z is normal, meaning bell-shaped, with a mean of 0 and a standard deviation of 1. That's not the author's notation, that's my own notation. I think it's pretty clear. Alright, so if I draw this standard normal distribution, I've got a bell-shaped curve, of course, and all this means is the bell peaks at the mean of 0. I can even indicate it like that. Alright? Now, the standard deviation being 1, that's not so easy to interpret graphically, but certainly we can see the bell peaks at 0. And remember, this horizontal axis represents all the possible z values, theoretically between minus infinity and positive infinity. Alright, let's say we've got a standard normal, and I want to compute the probability that a z, any z, lands between certain limits of interest. So let me ask you to consider that. Find the probability that z, well, let's start out nice and easy. Find the probability that z, a randomly selected z value, would be between 0 and 1. Well, all I really need to do is use techniques of calculus to find out the area of the standard normal curve between 0 and 1. That is this probability. Write that down. This is the total area under curve, or let me not the total area, don't let me mislead you. It's the area under the z curve between 0 and 1. I'll just abbreviate that in formula as area under between 0 and 1. And again, we don't have the tools of calculus widely at our disposal in this course, so we're going to use the Texas Instruments calculator to grind out this area for us. All right? What we're going to do is use a new function called normal CDF. As you might expect, it's located in that distribution, in that distribution menu, same place we found binomial PDF and binomial CDF in Chapter 5. We'll press the second vars command, get to the second level above the vars button. Of course, that's the distribution operator. And I believe it's on the TI-83, it's function address number 2 in that list. You'll see it. Normal CDF command. It'll open up this command in your home screen. Right. Now the syntax of this normal CDF command is very simple. In the standard normal case, you just plug in your left boundary of interest and your right boundary of interest, and it will give you the total area under the z distribution between those limits of interest. So in this particular case, if I'm interested in the probability that a randomly selected z variable is between 0 and 1, I'll use my normal CDF command. I plug in the left boundary of 0 and the right boundary of 1 and hit enter, and I get 0.3413. Couldn't be simpler, right? So this tells me the probability that a randomly selected z value is between these limits of interest is indeed 0.3413. Okay? Alright, I want to do an example out of the book, and let me cite the example here and ask you to pause to read through the example and familiarize yourself with it before you go on. I want to do example 3 on page 255. Alright, so please pause now and familiarize yourself with that example, and come back when you're ready. Alright, we've got a situation where we're looking at a large group of thermometers. The ambient temperature is 0 degrees Celsius, and, well, the idea here is some thermometers read a little too high, some thermometers read a little too low, some are right on the money. The idea is that these events happen with different probabilities. So the thermometer readings the book tells us, have a normal distribution. Oops. The collective group of thermometers readings, we will let be the variable z, because we know, the book tells us, it's a normal distribution with a mean of 0 and a standard deviation of 1. It's always a standard normal, okay? Now the book asks us, find the probability that a randomly selected thermometer from this group will read 1.27 degrees Celsius or less. Okay? So again, I don't have a left boundary, or at least a listed left boundary here. What I can do is use my TI-8384 to grind out this probability in this fashion. Well, we need to plug in a left boundary and a right boundary. Well, if you're less than 1.27, what does that mean? Well, less than 1.27 technically means between 1.27 and negative infinity. Notice there's no left boundary of interest here. Well, the idea here is, how do we plug in a value of negative infinity on our TI calculator? Now, if you look, if you read the fine print of our book, you'll see that the author wants us to use minus 99999 to approximate negative infinity. Alright, I suppose that's the best we can do on our calculator, so we'll use normal Cdf command under the distribution menu, and I'll just put that in for my left boundary like our author indicates, and 1.27 for our upper bound of interest, and I plug this out and I get 0.8980. Alright, so this indeed is the probability that a randomly selected thermometer in this experiment will be less than 1.27. I can make a quick sketch of that scenario, indicating that the total area under the standard normal curve below 1.27 is indeed 0.8980. So the calculator makes it easy for us. Alright, I want to do another similar example, and actually it's the next example in the book, so I'm going to do example 4 on page 256. Please pause now, familiarize yourself with the problem statement, and come back when you're ready to go. Alright, so again we're in the same situation. We've got a large group of thermometers. It's 0 degrees Celsius outside. Some of the thermometers read low, some of the thermometers read high, most are somewhere in between. In the long and short of it, we've got a standard normal. In other words, a normal distribution with a mean of 0 and a standard deviation of 1. Alright, in this example, we seek the probability that a randomly selected thermometer is greater than minus 1.23. Well, what does greater than minus 1.23 mean? Well, I can demonstrate this graphically. Remember, the horizontal axis represents all possible z values between negative infinity and positive infinity. Minus, remember, the mean is 0. Okay, so this standard normal is always going to peak at 0. Minus 1.23, I'll mark this down here somewhere. So really I'm seeking for the total area under this standard normal curve to the right of minus 1.23. Alright, so again, this is equivalent hang on a minute. Alright, this is equivalent to this statement. If z is greater than minus 1.23, I can symbolize it in this fashion, where z is greater than minus 1.23 and less than positive infinity. And as you might predict, our author is going to want us to use 999,999 as our best approximation for positive infinity, using the normal Cdf command. Alright, so we'll obey our author's instruction. So go to your distribution menu. Oops, I should have put CDF in here. Let me rewrite this. Using the normal Cdf command on our TI-83 calculator. I plug this in, and I get 0.8907. Alright, so that tells me the probability that z, a randomly selected standard normal value, is greater than minus 1.23 is going to be 0.8907. Alright, so that's examples 3 and 4 out of our text. Alright, I want to do another example out of the book, and actually it's the next example, example 5. This is also on page 256. So please pause now, familiarize yourself with the problem, and come back when you're ready. Alright, here, again, it's 0 degrees Celsius outside. We take a randomly chosen thermometer from a large group of thermometers, and we want the probability that a randomly selected thermometer reads between minus 2 degrees Celsius and positive 1.5 degrees Celsius. Alright, well, we are now expert in using this normal Cdf command in the distribution menu. So here we do have two explicit values of z listed. Minus 2 is our lower bound, 1.5 is our upper bound. So simply plug in these values, and the probability that the thermometer has readings between these limits is going to be 0.9104. Again, I can symbolize that graphically. If I've got a bell-shaped distribution with a mean of 0 and a standard deviation of 1, well, minus 2 is somewhere down here, left of 0. 1.5 is up here, right of 0. The total area under the curve equals 1. So I claim the area between these limits of interest, according to the techniques of our calculator, is 0.9104. Alright. There's one more subtopic we have to cover before we call it a day. And before I do that, I want to review what we've done in the last 3 examples. Because what we're going to do now is to work things in reverse. In the previous 3 examples, examples 3 and 4 and 5 in the book, we were given z-score limits, and we're asked to find probabilities. Okay? The answers to the previous 3 examples were indeed probabilities. Now we're going to work things a little bit in reverse. Let me write that down. Now the reverse. We're going to be given probabilities. and we're going to want to find the z-scores that determine those probabilities, again in the standard normal case. To do this, we're going to use the inv norm. Hang on a minute. The screen's jumping around a little bit. We're going to use a command on our calculator called inverse normal, or invnorm command. And I'm going to need a new screen, and we'll do a few examples of this. Hang on. Alright. I'm going to work out another example in the book. Example 6 on page 258. Please take a minute and pause your video to familiarize yourself with this example on this in the text, and come back when you're ready. Please pause now. Alright, again we're in the normal, in the standard normal distribution. Z represents all these different thermometer readings, and of course Z refers to a standard normal, a bell-shaped curve that peaks at 0 with a standard deviation of 1. The example asks us to find the Z value separating the top 5% from the bottom 95%. And essentially they're asking for the z-score, the thermometer reading that is in the 95th percentile. In other words, that's greater than 95% of all the thermometers. Alright, well, pictorially, the book urges us to draw pictures in these types of applications. We've got a standard normal. Right? It's a bell-shaped curve that peaks at a mean value of 0. Again, the horizontal axis represents all our possible thermometer readings, technically from negative infinity to positive infinity. And I claim there is a thermometer reading that we have to find such that the probability of being less than this reading is 0.95. And the probability of being above this reading is 0.05. Alright, so essentially we want a z-value such that the area to the left of that z-value is 0.95. Remember, the total area under the curve, under the standard normal curve, is 1. Alright. So what we'll do is use the inverse norm command. And for this command, well, for this particular problem, all you've got to plug in is the area to the left. Now that's the way the TI-83 is set up. Under the standard normal, you plug in the area to the left, and you should be able to grind out the proper z-value, again using techniques of integral calculus that are really beyond the scope of this course. So again, you hit your second vars command to get to the distribution menu, and I believe it's the third one on the list, inverse norm command. And again, for this particular problem, I'm going to plug in an area to the left of 0.95, and it will automatically grind out the z-value such that the area to the left is 0.95 and it's 1.645. Alright, so we can go backwards also. Now remember, this is area to the left of a particular z-value in the standard normal case. Alright. Let's do another example. This one's not in the book. Again, in the same situation, Z is a standard normal with a mean of 0, with a mean of 0 and a standard deviation of 1, I'll say find the z-value, or the thermometer reading, that separates, well, let's say the bottom 40% from the top 60%. I claim that such a thermometer reading exists. Pictorially, if I sketch a quick graph of the standard normal, the thermometer readings will peak near 0. Well, if you want to cut off the bottom 40%, well, clearly because of symmetry, 0 cuts off the bottom 50% from the top 50%. So this score that cuts off the bottom 40% has got to be less than 0. Hopefully you can believe that without too much arguing. Again, 50%, well, 0 is the median, so that means half the data is below 0, half the data is above 0. So cutting off the bottom 40% puts me left of 0. So all I really need to do is use my inverse norm command. Again, it will spin out the z-score, which cuts off an area of whatever you plug in here to the left, right? If my area to the left is 0.4, I don't really need this. The area to the right is 0.6. Remember, you've got to plug in the area to the left to find my z-value here of interest. So I'll do inverse norm 0.4. And I plug that out, and I get a minus 0.2533. That is the z-value I seek. Now, of course, because you're left of 0 in the diagram, you're going to expect that this value is going to be negative, right? Anything that cuts off an area less than 50% or 0.5 is going to correspond to a negative z-value. All right, we'll call it a day. We're at about 43 minutes, and we'll follow the usual protocol for Online Exam 9. And this concludes the lecture, the Online Class 9 today.